Welcome to the final section of Chapter 2. We have 2.3. We're going to look at Venn diagrams and set operations. So our Venn diagram is a picture of our set. And most of the time, we're not going to write anything in our set. It's just the concept of our set. So here, our box is our U or universal set. It's all possible things that we're talking about. Sometimes we'll define this explicitly, sometimes we won't, just depends on the example, if we need it or not. But if we were looking at, say, the numbers 1 through 10, we can't have an 11 in our universal set because 1 through 10 are the only possible things we're discussing for that. So just depends on what we're looking at. We have a circle in here, and that is our set. So I like to color things in. I'm going to have my set A be this big yellow circle. So if I'm in A, then I'm in that set. If I'm not in A, I'm on the outside. So if we're in A, we're here. If we're not in A, we're out here somewhere. And we call this outside part a complement. Whoops. Or A with a little dash. This is all elements that are in U, but not in A. So it's the outside of the box, or outside of the circle in the box. So anything that we're not in our particular set is in its complement. So very useful. Other subsets or other type of Venn diagrams we can see for sets. If we want a subset, this is set B and this is set A. We have A is a subset of B, since everything inside set A is also inside set B. So that's what a subset would look like. We also can have independent sets. Whoops. These would be independent. A and B share no elements. That happens sometimes. We also have sets that cross a little bit, and we'll discuss these a little bit more. And the centerpiece here, colored pen. That's the piece that's in both sets. So that is in set A and in set B. I'm going to erase that. So we'll talk about that portion as well. So let's see. We talked about complement. Let's look at intersection first, which is what I just showed you. So intersection, we say A intersection B. So I think of that as either an upside down U, kind of, or an N without the extra little tail. Looks like a hat. Sometimes people think of this. And this is X such that X is in A and X is in B. So it's the set of objects that is in A and is in B. So it's in both sets. And if we want our picture, kind of have it above, but another one is good. Oh, those are nice circles, mostly. Okay, here's my set A. Here's my set B. And this is my intersection. This is the piece that both sets share. So if we're in this part, we're in both sets at the same time. I need to not color that all in. I'll have too much fun. So they overlap. If you think about an intersection on a road, where's the intersection? Well, it's when street A and street B cross each other. There's this middle piece that's technically on both streets. So that is our intersection. They cross over. Really important word here is and. So and means they're in both. I will do an example in a sec. I want to introduce our other term first, and then I'll do an example of this one. We also have a union, and we say A union B. It's literally the same symbol but flipped over. And we would say X such that X is in A or X is in B. So it can be in A, it can be in B, it could be in both. So our picture starts out the same. Here's my set A, here's my set B. I'm going to use the highlighter this time. If we're in the union, we can be in set A. So all of that is in A. Or we can be in set B, which we would color this part twice, but we wouldn't count it twice. So that's our union. Think of union as accepting everybody. So everybody from team A comes and everybody from team B comes, and we're all in this yellow circle together. So we bring everybody in. So union and intersection are similar, but they're different. I find people understand the intersection easier because it's easier to exclude things, like that definition is a little nicer. Union is everything comes along, so the or tends to throw people off. But just think of union as accepting. We bring all the things. Intersection is the part they only have in common, so only the part that they share. Okay, let's look at an example. We have set A, and this is 7, 8, 9, 10, 11. Set B is 6, 8, 10, 12. Set C and our universal set is 1 through 12. So we don't think of anything that's smaller than 1 or bigger than 12. So, and let's say A union B. There's multiple ways to do this. There's multiple right ways to do this. One way I like to show people when we start learning these is to look at set A first, write down everything in set A for a union. So I have 7, 8, 9, 10, 11. Okay, once I get set A down, I look over at B. What's in B that's not already listed in our union? Well, 6 isn't there. 8 is, 10 is there, but 12 is not. So anything that's in B that we haven't already written down, we write down for our union. So those are the things that are in A or they're in B. If I want A intersection B, now I go through and look, what do they both have? So I'm going to highlight these and then erase them. So it looks like they both have an 8 and they both have a 10. So I can highlight that. And we should have the same number of highlights in A and B or else we didn't get everything. So I would just say 8 and 10. That's the intersection. Oops, I'll fix it. So that's the difference between those. While we're here, let's find A complement. So for this, I look at A and I look at my universal set. What is in my universal set that's not an A? Well, anything less than 7. So 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11 are there, so 12 is the only thing not listed. We haven't really played with set C yet, so let's do that. In doing this, we're going to make a slightly more complicated. I'm going to scoot these over so I have more space. Let's scoot you way over here. Nope. All right. All right. So let's say A intersection B union C. So when we have parentheses or brackets or braces or anything with our problem, we're going to do this just like our regular order of operations. We do what's inside the parentheses first, and then we do the extra thing. So this says take A intersection B, then union that with C. What's nice is we already have part of this written on up above. So A intersection B is 8, 10, union. I can either write the letter C or I could list what's in C, and I like to list what's in C. Okay, now I take the union of these two sets. It's just everything written there. 8, 10, 1, 3, 5, 7, 9. So order of operations are important for these. Practice these, write down lots of steps if you need to. That tends to help with these. Don't try not to do them all in your head. That's a good way to mess these up, and that's frustrating when that happens. A couple things to note. A intersection empty set. So what is an A that is also in the empty set? Well, the empty set is empty. There's nothing in it. So A and empty set share nothing. So draw a picture of that if it helps. We can also think of a union empty set. We bring everything from A and everything from the empty set. So everything from A is A. The empty set has nothing in it. So we just get A. So just a quick thought exercise on that. Okay, we have one last rule. We're really going to get into an equation for the first time in these sections. This is called the union rule. Or inclusion, exclusion. I've seen it called both. It tends to be on the 100 levels and 200 level math classes. We call it the union rule. The higher level math classes, you call it inclusion, exclusion. I was embarrassed the first time I took one of my higher ones because I didn't know what inclusion, exclusion was, and they had to explain it to me. I'm like, oh, I called it a different thing. That's good to know. So I wanted to share that with you. This is if we want to count the number in A union B. So the cardinal number or n of A union B equals, we take the number in A plus the number in B minus, so it couldn't have been that easy, the number in A intersection B. I'm going to do an example of this, but can you think of why we would have to subtract something when we're trying to gather how many things are in it? Well, if you recall our picture, A and B. So if this is my set A, I'm adding all of these things here. I need another color. Ooh, that's a nice color. This is a set B, which I'm adding all of these things here. What about that green area? Because yellow and blue make green, of course. Well, we've added those people in the green area twice. So they're not listed there twice, they're only there once. So we have to add, or excuse me, subtract off the doubles. So that's where that extra subtraction comes from. So if we think about this, we have set A, people who like cats. Set B, they like dogs. So it is possible to like both cats and dogs, and it's also possible to only like cats or only like dogs. So let's look at a slightly more real world example. Well, sort of. So set A, we have 4 people. Ashley, Josh, Emily, and Jake. These 4 people in our little survey like cats. We also have Jake, Ethan, and Hannah, who like dogs. Now you'll notice we have somebody listed twice. So if we want to use this principle, we have the number in A, number in B. There's 4 in A, 3 in B. So we're going to say, hey, how many people took our survey? And if we were to just count, we would get 7 people. But we can see that Jake is listed twice, so we have to subtract off Jake. So, number in A, union B. So how many people took our survey? Well, we have, I don't need to write that. The number of A is 4, plus the number in B is 3. Square screen. Minus, how many people are in both groups? Well, just Jake. Minus 1. That's going to give us 6. So we took a survey of 6 people, and we could see them where they are. So when you find the union of something, you want to make sure you haven't counted anyone twice. That's going to give you faulty data. So, all right, that is the end of chapter 2. So hopefully that helps. If you need something different than what I'm giving you, let me know. And I will see you in chapter 3.